Greetings YouTube and welcome to Zeen Chemistry. I'm super excited to present you guys the very first episode of the series about Shapiro's reaction. We're gonna kick things off by talking about the general reaction mechanism. We're gonna be pushing those arrows as to see what's going on in this reaction. Then we'll talk about experimental tweaks and the changes that were made to this original reaction as to optimize it. Then we'll talk about reaction controls and what product you should be getting out of this one and all the particularities that are involved. Then we'll talk about literature examples and what was actually done in the lab about Shapiro's reaction. Then we'll do a synthesis exercise that I prepared as to check if you guys got it all. So let's jump right into it. Alright, so before getting into details about the reaction mechanism, let's talk about the general reaction. So this molecule, which is a tosyl hydrazone, tosyl is this, the hydrazone part is this, with two different substituents on it, will react with two equivalents of N-butyl lithium to create the vinyl carbanion, which is this molecule. Then this vinyl carbanion will react with any electrophile in the media to create this new bond between the carbon and the electrophile. Alright, so now that we've seen the general reaction, let's jump right into the mechanism. So first of all, a ketone will react with an Arene sulfonyl hydrazone. As I said in the general reaction, we have a tosyl group, and the tosyl is this particular leaving group, which is a sulfonyl, and a toluene part, which is a benzene with a paramethyl, which is represented by this TS, or tosyl. So the ketone will react with this Arene sulfonyl hydrazone. The lone pair of electrons on the nitrogen will react on the carbonyl, and the oxygen will take the electrons and use them to make a proton transfer and take the hydrogen, which in this case is the yellow one. Could have been either one. So it takes this one, which is now here, and it can easily take another one because the lone pair of electrons on the oxygen can grab any hydrogen in the media. And then you can remove or force the removal of water with, for example, Dean Stark. And then you generate this guy, which is our tosyl hydrazone that we wanted from the start. Alright, so now that we have our hydrazone, we can add two equivalents of N-butyl lithium. The first equivalent of N-butyl lithium shall react with the most acidic proton, which is the one located on the nitrogen, because the anion can be easily stabilized by the toluene sulfonyl and the induction of the nitrogen. Therefore, we get this first anion on the nitrogen. Afterwards, the second equivalent of N-butyl lithium will react with the second most acidic proton, which we can say is the one on the CH2 part of the molecule. Therefore, we create this intermediate, which is a dianion because it's got two negative charges. Of course, since it has two negative charges, it doesn't last for long, and the orange arrows occur. So we form this double bond, and this double bond was between the nitrogen and the carbon, go between the two nitrogens, and therefore you eject the toluene sulfonyl, which I said was a good leaving group. So you get this molecule, and you still have this negative charge on the nitrogen. So the electrons can be placed in between these nitrogens, and you create dinitrogen, which you know is a good leaving group. So you can gas it out of the solution, and you end up with this vinyl lithium molecule. And if you have any electrophile in the media, you can form this final molecule, which is what we wanted to do in this Shapiro's reaction. Alright, so in the mechanism part, I said that the second equivalent of N-butyl lithium would react with the second most acidic proton. But you're right if you ask yourself, what is the second most acidic proton? Is it really these hydrogens? Why couldn't it be those? Well, you're right, and if you only use two equivalents of N-butyl lithium, you're gonna end up with a mixture of two dianions. So you're gonna get the ones where you deprotonate the ortho hydrogens on the toluene sulfonyl part, and the ones where you actually deprotonate the ones that will lead to the alkene. So this is because the orthohydrogens are kind of acidic, since the anions are stabilized by delocalization in the toluene sulfonyl group. So to optimize this reaction, chemists have found that if you use Trisyl instead of toluene sulfonyl, you can get better results. Trisyl is also known as 2,4,6-tri-isopropyl benzene sulfonyl. So you replace these orthohydrogens by 2 isopropyl groups, and you add 2 carbons to this part of the molecule. So this makes that you only have to use 2 equivalents of N-butyl lithium instead of more than 3. Because if you're using toluene sulfonyl, often in the literature you'll find that they use an excess of base and they use more than 3 equivalents. But by using Trisyl, you only get to use 2, because the second most acidic proton in this case is this one, or this one, either of those. So you get your dianion, and then you can create your vinyl lithium molecule, and then add your electrophile, and then get your final product. So by using Trisyl instead of toluene sulfonyl, you get to only use like a small excess of N-butyl lithium, about 2.05 in the literature. And also by doing that, you increase the reaction rate, since the bulkiness of the isopropyl groups makes the intermediate much less stable, and therefore it accelerates the reaction, which is shown here again. A few particularities about this reaction is that the reaction is under kinetic control, which means that the product that forms at the fastest rate is the major one. It is an irreversible reaction, and it favors the less hindered alpha hydrogen, alpha being the one adjacent to the C double bond N group. Generally, the less substituted alkene is highly favored, like 50-1. And if you have unsymmetrical hydrozones at the beginning, the trans alkenes are favored. And usually, like in every reaction that is under kinetic control, you do it at low temperatures. So literature example I found is about the reduction of ketones, which shows how the ratio of kinetic and thermodynamic product is obtained. So it was done by Shapiro himself. You start with a ketone, you add toluene sulfonyl hydrazone in solvent, you get this hydrazone, and then when you add 2 or probably more equivalents of methyl lithium, you get 98% of the kinetic product and 2% of the thermodynamic product. The kinetic product is the one that's formed the fastest, and as you can notice, it's not the most substituted alkene, so it's not the most stable, and the thermodynamic is, the most stabilized, and it's the one that's formed in the least amount. So as I said earlier, you usually prefer the less hindered alpha hydrogen, because if you don't, nucleophilic substitution are in competition with this reaction. So there are very few cases where you can use a tertiary alpha hydrogen, which is very hindered, and use Shapiro's reaction to yield good results. But if you're using benzylic hydrogens, which are pretty acidic, you can obtain pretty good yields. Like in this example, where you start with this ketone, you use your hydrazone, and then you get your hydrazone added in replacing the ketone. And then by using 2 equivalents of LDA, and right after you use H2O, you get to obtain this alkene and to add your hydrogen from the H2O, which in this case is your electrophile. So here's another example where Shapiro's reaction was used. This one was used as not to get any epimerization and to get the molecule itself. So it starts with a stereogenic center here, which is R. And you add the hydrazone to it. and you get this hydrazone molecule. Normally, it would epimerize 150 times faster than the ketone equivalent you had at the beginning, this one, and in the presence of any acid, because the nitrogen's basicity is much higher than the oxygen's. And when I'm talking about epimerizing, if you're not familiar, the any base in the media could grab it in hydrogen, eliminate, and give this carbon, render this carbon sp2, so it does not have any 3D orientation. And this alkene could grab back this hydrogen, it's in an equilibrium, and yield this S stereogenic center. So it's an equilibrium between these two. So normally you'd get a mixture of both. But since you're using Shapiro's reaction with these specific conditions, you're using 5 equivalents of N-butyl lithium. So you're using a major excess. As we've said, you need like 2 or 3 since this is toluene sulfonyl. And you're using TMEDA as solvent. So you're making sure that there are no traces of acid whatsoever in the media. So you get your vinyl lithium molecule. And as I said, you can add any electrophile to the media and make it react with the vinyl lithium molecule. So there, they added the iodine and they made this molecule with this particular set of groups. So they replaced the ketone for an alkene with an iodine next to it, which is pretty interesting. Another use of Shapiro's reaction is to introduce radioactive isotopes into your molecule. So you can do some isotope marking. So in this example, they started from the ketone of this molecule. They added their Trisyl hydrazone, which we're getting familiar with. And as you can see, they use only 2.2 equivalents since it's Trisyl, so they don't have to use an excess of 3-butyl lithium. And they are in kinetic conditions, so low temperatures. And afterwards, they added tritiated water, so T2O, and they introduced this tritium atom, which has high specific radioactivity and radiochemical purity. So this last example is about the catalyzed version of Shapiro's reaction, which is using this particular hydrazone and LDA as your base and in ether and kinetic conditions. So by using this, you get mostly the cis alkene, like more than 99% of cis alkene over trans. And this is because of the chelation of lithium by the nitrogen. So this orients the lithium in such a way that you get the cis alkene and not the trans, because this happens, this intermediate. So I know I have not explained it in full details. You can look up into this reference. It's pretty interesting if you ask me. Alright, so let's wrap this up with a quick synthesis exercise. So what if you started with this molecule and you wanted this final product? And I'm hinting you guys by this first reaction, which you could have used plenty, but I'm telling you, you can do it with this Jones oxidation. I know this is the first video, so I haven't reviewed Jones oxidations yet, but I'm telling you, it's an oxidation, so this should give you a big hint. So you have this reaction, and you do another one, you get this, another one, you get this intermediate, then you add something, and you get this yellow component to your molecule. So I'm gonna let you guys pause this video and try it for yourselves if you like, and then I'll give you guys the answers. Alright. I'm gonna leave you guys a few seconds. Alright, so you're probably unpaused by now. So let's start things off by doing Jones oxidation. So you transform the alcohol into a ketone, which if you Google Jones oxidation should be pretty obvious. So you get this ketone. And what else could you do to get this molecule? So you've noticed that you've created a double bond and you added an electrophile, and it's in the least substituted place, which you had no choice really because there were no hydrogens here. I made it easy for you guys. So if you add a Trisyl Hydrazone to it and ethanol, remove the water, you get your Hydrazone here. And if you add a slight excess, more than a 2.0 equivalence of a N-butyl lithium, in this case 2.2, then you get this molecule, which is your alkene with the lithium, your vinyl lithium molecule. And you could isolate this molecule, but if you have any traces of electrophile, it will react. So you better add your iodine, pretty quickly, so you get this final molecule. So I'd be pretty interested in knowing what you guys would do with this final molecule. What kind of lever it would create in the synthesis. You could type it in the comments. I'd be glad to know. I could make a future video about it. You guys tell me. So yeah. Alright, so I guess that pretty much sums it up for the first benzene chemistry video about Shapiro's reaction. I hope I could have helped some of you guys. The references are in the description below. Please take note that one of the links is particularly important in Science Direct. I took most of my info there, so I'll go ahead and check this out. This was my first video. I'm sorry for the French accent. I'm French Canadian. Yeah, I did my best. And also, if you have any tips or way that I can improve, just feel free and share them in the comments. If you'd like to subscribe and like, go ahead. And I guess I'll see you guys in the next one.